We are now ready to determine the electric field from various charge distributions that we've already looked at. And let's start with a conducting sphere. So here is a conducting sphere. Think of it as a solid metal ball, if you will. Radius r, charge q. Now I don't show the charge in there yet. I will momentarily. Some initial considerations is the following. First one really important. From electrostatics, now, electrostatics is the condition, the electrical condition of an object that is in electrical equilibrium. A long time has passed, and it's sitting there with a certain amount of charge. And that charge is in a particular configuration. And it's in that particular configuration for a very good purpose. In this case, the E field is 0 everywhere inside the conductor. And there's a very simple reason for that. And that reason is that if it was not true, the charges would move. And now you ask, but why, oh why would the charges move? Well, the charges move because E fields are what put forces on charges. In particular, the electric force is EQ. So if the charge is there, and by the way, in a conducting sphere, the charges are there. There are free charges. Think of them as electrons, or you could charge this positively. And there's positive charges, free to move around. And if there's an electric field, that times the charge is the force on those charges. And really that's the net force because gravity is not of concern here. So that Fe, in order to be 0, has got to have the E be 0, the electric field be 0. All right, so just kind of looking at what happens here. Here's a conducting sphere. And notice there's positive charges distributed around the interior of this conducting sphere. Well, what happens? The E field is not 0 in this case. So immediately we will achieve electrostatic conditions. And the way that happens is the charges quickly migrate to the outer surface. That is the condition by which the electric field will go to 0. And it is the only configuration where that's true. So now Fe is equal to EQ, and that's 0. The E field has gone to 0. I could explain that more, but we'll encounter that again. So charges, electrostatics, charges rearrange themselves very quickly because nature tells them to. And they go into the places they need to be, so the electric field is 0. So in this case, they'll uniformly distribute themselves on the very outer edge of the sphere. Uniformly distribute themselves. And again, this is only true for a perfect sphere. Other geometries, it won't necessarily be true. So in our big conductor here, we had the charge Q, and we saw how they just moved out to the outer edge. And now we're putting a Gaussian surface around the entire thing. Remember, the Gaussian surface is a mathematical surface that is there for our analysis, which we are subsequently going to do. So little r is the radius to the Gaussian surface. And now we're going to put another Gaussian surface of a random shape inside, contained inside this solid conducting sphere. These are both Gaussian surfaces. We can put these things anywhere we want. And if somebody tells you you can't put it there, you can tell them, oh yes I can, just watch me. So the Gaussian surface inside the conductor is of concern at this very moment. If the electric field is 0 everywhere on the Gaussian surface, and it is, because if not, the E field is not equal to 0, then it moves the charges around, and that takes work, and there's a change of energy, and it all goes through its paces very quickly until there's no electric field. So the consequence of that is that Q enclosed is equal to 0. Because if Q enclosed by this Gaussian surface is not 0, then there will be an electric field on this Gaussian surface. And there can't be. So the net charge inside the conductor has to be 0. And that's going to be true anywhere inside the material of the conductor itself. Now, a sphere is so wonderful, partly because it has spherical symmetry. Symmetry is a very important concept, And it just says that there's ways in which you can consider it that it doesn't change. Particular in this case, no preferred direction or charge distribution in the three-dimensional space it finds itself in. So we could put an axis of rotation here and spin it about this axis, and you couldn't tell any difference in the charge distribution on, or the electric field coming from this sphere. You could put the axis like this and rotate it around that axis, or you could punch an axis of rotation right to the center and rotate it about there. No matter which way you rotate it in 3D space, no change in the observables from an external point of view. The E field is radial. It's another thing it is. Everywhere on the surface, it's radial. And it's uniform. It's the same size everywhere on any spherical surface that's concentric with the conductor. So that means that this Gaussian surface has a radial electric field that's concentric, that's coming from the center, essentially, and the electric field that passes through that Gaussian surface is of constant value and radially outward everywhere on that surface. Okay, so sorry, I don't like spending over 6 minutes on a slide, but sometimes it just has to happen because some of those concepts were really important to get across. So here is our conducting sphere, charge Q, radius r, and our Gaussian surface is at radius little r. This is a variable, essentially. So remember, the Gaussian surface is a mathematical region. It doesn't consist of any material substance. Now the electric field, uniform on the surface and perpendicular to the surface. What surface? We're talking now about the Gaussian surface. Same size and perpendicular to the surface. Wonderful. So we're going to apply Gauss's law, at least part of it. The integral in Gauss's law is the closed integral of E dot dA, or E perpendicular dA. These are vectors. But because it's uniform, the E field is uniform and radially outward, the E field is in the same direction as the area vector, the dA vector, and it's constant. So it's just simply electric field, constant value, integral of dA over the entire surface, 4 pi r squared. Very easy. So we've just evaluated the integral. And now, recognizing that the value of that integral, which is the electric flux through the closed surface, which is the Gaussian surface, is Q enclosed over epsilon 0. That's the rest of Gauss's law. But we know what Q enclosed is because it's all of it, and all of it is Q. So Q over epsilon 0 is the answer. Then, at the sphere surface, we can now solve for the electric field. Here it is. It's just equal to this ratio. And we can just divide by 4 pi r squared. So 1 over 4 pi epsilon 0, Q over r squared. What does that look like? Well, it looks like a point charge at radius r. Which is exactly what we would expect it to look like. Now notice that, I'm sorry, just to clarify, this is at the surface of the sphere. And I think I was just directing you to the Gaussian surface. At the surface of the sphere, the radius is r. So at the very edge, the outer edge of the surface, we have big R. So it's kq over r big R squared. Outside of the surface, same flux passing through the Gaussian surface. And it's little r. So you look at little r here, and this is the variable. At the surface, it's big R, because that's the definition. Outside of the surface, the edge to the Gaussian surface is little r. So now we can graph the electric field in all of space. The electric field takes a certain value from 0 to big R. And we've already defined what that is. Up from 0 to big R, it's 0. So we just graphed it. And then, as soon as we get to the outer edge of the sphere, it suddenly spikes to the value given here at the surface, and then subsequently it obeys this inverse square law. So there it is. And the value here, just to clarify, is 1 over 4 pi epsilon 0 q over big R squared. And that is the electric field from the spherical conductor in all of space. Now we're going to find the electric field from a line of charge, but we're not interested in the finite line of charge. We're actually interested in an infinite line of charge. We're going to use Gauss's law, and you might ask, well, how are we going to put a Gaussian surface around an infinite line? Well, we don't need to. In fact, this yellow region here is the Gaussian surface we're placing around this line of charge, and it's a finite Gaussian surface. So let's see how this gives us the electric field produced by the line of charge. Radius r to the Gaussian surface. So that's little r, it can be any value. The length of this we'll just call L. Now here's an area patch on the wall of the surface itself. So this is our differential area vector. And wonderfully, as you may already be recognizing, if the E field is in the same direction, that's marvelous, because then the dot product is just multiplying the two together. So that in fact is the case, because the electric field produced by a line of charge is radially outward from the line. So E perpendicular is E. It is constant in value everywhere on the wall of this Gaussian surface, and it's radially out from the wire. So the flux, the electric flux through the Gaussian surface, closed integral of E dot dA. So as we need to consider the entire closed integral. So that's going to be the electric field of the wall times the area of the wall. And that, by the way, is equal to the electric field of the wall, which is a constant, times, well, what's the area of this wall? Well, it's the circumference, 2 pi r, times the length. That gives the area. So there it is. But there's something else. There's the ends. So these end caps have to be considered as well. There's one hidden over on this side to make it a closed surface. Well, this is easy because the electric field on the ends, there's two of them, so multiplied by 2, pi r squared is the area of the ends. But what is the electric field through those end caps? We need to consider that. Well, the combined flux is Q enclosed over epsilon 0. So the flux through the ends, well, the electric field doesn't go through there at all because it's radially diverging off that wire. So the E field through the ends is 0, therefore the flux through the ends is likewise 0. So the entire flux reduces to this. So E of the wall, 2 pi RL, is Q enclosed over epsilon 0. Let's solve for E. Very simple. E is Q enclosed over 2 pi RL epsilon 0. Well, what is Q enclosed? Q enclosed is not the entire charge of an infinite line, because that would be infinity. Rather, it's the amount of charge enclosed by the Gaussian surface. So it's very, very finite. Well, this has a uniform linear charge density, lambda. So it's just lambda times the length gives us the charge contained in the Gaussian surface. So lambda L over 2 pi r L epsilon 0. L's go away, and here is our answer, which should look familiar because we've already solved for the E field from an infinite line and got the same result. Very marvelous. Now, I took some explanation there, but once you get used to this, you can do it all very rapidly, and you don't even have to memorize this formula because you can derive it from an appropriate Gaussian surface around the wire. You can do it much more rapidly than I just did. But now we can also evaluate the electric field in 3D space. And what you see, this is an infinitesimally thin line, right? So we don't have to worry about the spatial extent of the wire itself. So it's just inverse r. Here's the variable. And so it's simply like this in all of space.